Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. IPv6 offers several ways for devices to obtain an address and join the network, and understanding each configuration method is essential for both managing a real network and passing the Network Plus exam. In IPv4, most devices are either set up manually or rely on DHCP to receive an address. IPv6 expands on this by introducing new automated techniques while keeping manual options available. These methods include static configuration, SLAC, which stands for Stateless Address Auto-Configuration, and DHCPv6, a newer version of the traditional DHCP protocol adapted for IPv6 networks. Each of these methods plays a specific role depending on the network size, policy requirements, and desired level of control. Some administrators want full control over who gets what address and when. Others prefer to let devices self-configure with minimal administrative overhead. The good news is that IPv6 supports both styles, sometimes even at the same time. You might find a router advertising its prefix using Slack, while a DHCPv6 server hands out DNS settings to devices on the same segment. This flexibility is powerful, but also requires a clear understanding of how each part fits together. But let's start with static IPv6 addressing. This method involves manually assigning a full IPv6 address to a device, just like you might do with IPv4. When using static addressing, you'll enter the complete address, the default gateway, and sometimes the DNS servers. This method gives you full control and ensures predictable IP assignments. It's especially useful for servers, printers, and other infrastructure devices where you don't want the address to change. However, managing static assignments becomes more difficult as the network grows, which is why it's mostly reserved for key systems rather than general clients. Next, we have SLAAC. This is one of the most important innovations in IPv6. With SLAAC, a device generates its own address using a combination of a router-provided prefix and its own interface identifier. The interface identifier is typically created from the device's MAC address or generated randomly, especially if privacy extensions are enabled. SLAAC allows devices to configure themselves with no need for a DHkey server. This makes network deployment simpler and is especially useful in environments with large numbers of client devices or frequent turnover, such as classrooms, public access areas, or mobile setups. SLAAC depends on the router's ability to send advertisement messages. These are called router advertisements, or RAs, and they contain important information such as the network prefix and flags, indicating whether SLAAC should be used, whether a DHCPv6 server is available, or whether additional configuration is needed. When a device sees a router advertisement with the autonomous flag enabled, it knows it can use SLAAC to create its address. If other flags are set, it may also contact a DHCPv6 server for DNS or other details. In this way, router advertisements help coordinate how clients configure themselves. Now let's talk about DHCPv6. This protocol is similar in function to the traditional IPv4 DHCPV, but it's been re-engineered for IPv6's structure and flexibility. DHCPv6 can assign full IPv6 addresses to clients, or it can act in a more limited role, just handing out DNS server information while leaving address creation to SLAAC. This split model is sometimes called stateless DHCPv6. On the other hand, stateful DHCPv6 keeps track of address leases, just like in IPv4, and provides clients with their full address and configuration. Network designers can choose which mode fits their environment best. In some networks, you'll see both SLAAC and DHCPv6 working together. For example, a device might generate its IPv6 address using SLAAC, then use DHCPv6 to get the DNS server settings. This is often referred to as a hybrid configuration and allows administrators to combine automation with centralized control. Hybrid configurations are common in large enterprises, where DHCPv6 can log lease activity and provide visibility while clients still benefit from the ease of automatic addressing. This flexibility also helps in transitioning networks, especially those gradually moving from IPv4 to IPv6. The choice between SLAAC, DHCPv6, and static configuration depends on the goals and size of the network. SLAAC offers ease of use and scalability, making it perfect for general-purpose client networks. DHCPv6 offers centralized control and logging, which is critical in corporate environments. Static addressing is best for infrastructure components that must be easy to find and connect to, such as servers, gateways, and DNS appliances. Understanding which method to apply and how to spot configuration mismatches is a common source of exam questions and real-world issues. When a device is using SLAAC, the IPv6 address will often show a prefix that matches the router's advertised network and a suffix based on the device's hardware, or a randomized value. If the network uses DHCPv6, you may see a lease entry or a client request visible in the server's log. Static addresses are easy to spot because they don't change and usually appear in the same format across multiple reboots or network connections. Recognizing these patterns helps identify whether address assignment is working as expected or if there's a misconfiguration. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. One of the key differences between IPv6 and IPv4 is how address privacy is handled, and this shows up most clearly in how temporary addresses are used. With IPv6, a device can generate multiple addresses for a single interface. Alongside its regular global unicast address, a device might also use a temporary address that changes frequently. These temporary addresses are created using privacy extensions. Their purpose is to help protect user privacy by making it harder for third parties to track a device across different sessions or networks. They are mostly used for outbound connections, like web browsing or accessing cloud services, and are not meant for incoming traffic or hosting services. Even though SLAAC and DHCPv6 both aim to assign addresses and settings to devices, the way they operate is quite different. SLAAC relies on router advertisements. The router tells the device, "Here's the prefix you should use." The device then generates the rest of its address automatically. In contrast, DHCPv6 is server-based. The client sends a request to a central server asking for an address and configuration. DHCPv6 can provide more than just an address. It can also assign DNS settings, domain search lists, and more. Depending on the flag set in the router advertisement, a device may use Slack alone, or it may be told to contact a DHCPv6 server as well. Interface identifiers are a major component in how IPv6 addresses are formed. These identifiers make up the second half of an IPv6 address. They are often 64 bits long and serve as a unique tag that identifies the device within the network. There are two main ways this identifier can be created. The first is through a process called EUI64, which uses the MAC address of the device and inserts a specific value in the middle to expand it. The second way is by generating a random identifier. This method is used when privacy extensions are enabled, helping to obscure the identity of the device and reduce the chances of tracking. When networks require control, logging, or fixed assignments, administrators often choose to disable SLAAC and rely entirely on DHCPv6. This centralizes address management and allows for the same sort of tracking and auditing that's common in IPv4 networks. However, in more open or rapidly changing networks like public wireless hotspots or educational campuses, SLAAC may be the preferred method. It allows devices to join and configure themselves with minimal friction. Understanding these trade-offs is important, especially when designing a network that needs to balance ease of access with administrative oversight. It's also important to know how address assignment interacts with routing. For example, even if a device receives a valid IPv6 address, it cannot send traffic beyond the local network unless it has also received the correct gateway information. This typically comes from the router advertisement in a SLAAC setup or from the DHCP IPv6 server if that's what the network is using. If either the address or the gateway is missing, the device may show as connected, but traffic won't leave the local segment. On the Network Plus exam, expect to see scenarios where you'll need to determine whether a configuration issue is related to address assignment, gateway configuration, or DNS. Troubleshooting IPv6 addressing can be made easier by knowing which configuration method is being used. If a device has an address that starts with FE80, that's a link local address, and it's automatically assigned. If that's the only address the device has, it means SLAAC or DHCPV6 failed. If you see a global unicast address that never changes, it's likely a statically assigned address. If the suffix part of the address looks like it includes the MAC address, that's a sign EY64 was used. If the suffix seems random and the address changes regularly, that usually points to a temporary address created for privacy. On the exam, you'll be expected to recognize not just how each configuration method works, but when to use each one. You might be asked to choose the best address assignment method for a high-security network, a mobile workforce, or a classroom full of laptops. Each of these has different needs. A server room might require static addresses for consistency. A large organization may use DHCPV6 to maintain logs and control. A public kiosk might rely on SLAAC to simplify setup. Being able to apply the right method to the right environment is critical for success both on the exam and in real-world design. In conclusion, IPv6 offers more flexible and powerful address assignment methods than IPv4. You can configure addresses manually for tight control, use SLAAC to let devices self-configure with help from the router, or apply DHCPV6 to distribute full settings from a central server. Sometimes networks use a combination of these approaches to strike the right balance between automation and oversight. Understanding how each method works, how they interact, and how to troubleshoot them is essential for anyone preparing for the Network Plus exam or working with IPv6 networks in practice. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.